This section is going to look at a topic called subspaces. And in particular, we're going to look at subspaces of Rn. So subspaces of all the vectors of n elements. So consider this set. And this time I'm going to define a set a little bit differently. I'm going to say that the set S is all of the three-dimensional vectors that satisfy this equation. So in other words, just writing that down, all the three-dimensional vectors that satisfy the condition 2s1 minus s2 plus s3 equals 0. So some examples of that is like the 0 vector, the vector 1, 2, 0, the vector 3, minus 1, minus 7, among many others. There's infinitely many vectors that are in that set. So you take, for instance, 3 minus 1, 7. Why is that in that set? Well, the condition for it being in the set says that 2 times the first element, so 2 times 3, minus the second element, minus 1, plus the third element, plus 7, has to equal 0. What does it equal? Well, this is equal to 6, so that's a minus 7. That equals 6 plus 1 minus 7, and that equals 0. So yes, that is in the set, and we say that the vector 3 minus 1 minus 7 is contained in S. Okay? But there are a lot of vectors that aren't in it. So for instance, the vector of 3 elements, 1, 1, 1, is not in the set S. And you can try that out yourself. Take those elements, 1, 1, 1, plug them into that equation, and you'll find that it doesn't work. It's not equal to 0. So that means that that vector is not in the set S. So let's look at some properties of S. So S, that's the set that we just defined on the previous page. So all the vectors that satisfy that equation. Now, let's take any two vectors that are in that set. So we have the vector u, which we're going to call u1, u2, and u3 as the three elements, and the vector v. So those are just any two vectors that are in that set. Because u is in the set, it satisfies 2u1 minus u2 plus u3 equals 0 by definition. Because v is in the set, it satisfies 2v1 minus v2 plus v3 equals 0. Because it's in the set, it satisfies that definition. But now what happens if I add them together? Take the vector u plus v. You add them together, you get that vector. What about that vector? What happens to that vector? Take the elements from this vector and plug it into the equation. So 2 times the first element in that vector minus the second element in the vector plus the third element in the vector. What do you get? Well, rearrange them a little bit. You get 2u1 minus u2 plus u3 plus 2v1 minus v2 plus v3. Well, we already said that that first part is equal to 0 and that second part is equal to 0, so the overall thing is equal to 0. What does this mean? That means that for the set S, if you take any two vectors that are in there and add them together, you get another vector that's in there. You can't get out of this set by adding vectors together. What about multiplication? We know how to do a scalar multiplication. So take our set S again, let U be anything in there, and let K be any number, any scalar number. U is in there, so it satisfies the equation 2u1 minus u2 plus u3 equals 0. By definition, if it's in there, it has to satisfy that. Now take u and multiply it by k. What do you get? Well, you get that vector. So what happens to that vector? Take the elements of that vector, put it into the equation, see if it works. That's what you get. Now rearrange it, take k out. What do you get? K times your original equation, which is k times 0, which equals 0. So again, just like addition, if you do scalar multiplication to any element in S, what happens? the vector you end up with stays in S. These two properties mean that it is closed under vector addition and S is closed under scalar multiplication. And these are the properties we look for a subspace. Now remember that set S was part of R3, but it wasn't everything. We had vectors in R3 that didn't satisfy that equation. But when we looked at the properties of it, we saw that if you add them together, add any two vectors in it together, you stay in S. If you do scalar multiplication, you stay in S. That is the definition of a subspace. So a subspace is a set, it's a subspace of Rn if it satisfies three properties. First is that the zero vector is in it. Well, that was one of the first things we saw, that the zero vector was in that set. The second thing is that it's closed under vector addition. So you take any two vectors in it, add them together, you stay in the set. Third property is that it's closed under scalar multiplication. So take any vector, multiply it by a number, you stay in the set. You can't get out of the set through addition or scalar multiplication. If those three conditions are satisfied, we say that it is a subspace of Rn. And note in our earlier example, S was a subspace of Rn. So let's work through another example. Take this set S. So S is all the vectors that have four elements, where the first two elements are any numbers, the second two elements are zeros. And is this a subspace? So to see if it's a subspace, we have to see if it satisfies those three conditions. So what's the first condition? The first condition asked, is 0 a member of S? Well, if we let S1 equals 0, S2 equals 0, then we have a vector V equal to 0, 0, 0, 0, and that is in S. So yes, the zero vector is in there. Second condition. Now, to show the second condition that is closed under vector addition, what we do is we say, let U equal to U1, U2, 0, 0, and V equal to V1, V2, 0, 0. Those are two vectors that are in our set S. Now we say, what about U plus V? So then U plus V is equal to U1 plus V1, U2 plus V2, 0, 0. What is this? This is a number, and two zeros. That is in S. So yes, the second condition is satisfied. What about the third one? Third condition is scalar multiplication. So we let U equal U1, U2, 0, 0, and we let K be a scalar. Well, then what happens if you multiply? Then K times U is equal to K times U1, K times U2, 0, 0. Is that in S? Sure, it satisfies that condition. So that is also in S, so that condition holds. So our set S is a subspace. The set S defined in this way is a subspace. You can't get out of it by adding things together. You can't get out of it by doing multiplication. It's a subspace. What about this example? The set S1, S2 in R4, where S1 and S2 are positive. Is this a subspace? Well, let's look through the conditions. The first condition is 0 in S. Well, the vector 0, 0, 0, 0, that is in S. So yes, the zero vector is in there. What about the second condition? So again, we say that u equals u1, u2, 0, 0, and v equals v1, v2, 0, 0. Then u plus v is equal to u1 plus v1, u2 plus v2, 0, 0. Is that in S? Well, since u1 and v1 are greater than or equal to 0, then u1 plus v1 is also greater than or equal to 0. And since u2 and v2 are greater than or equal to 0, then u2 plus v2 is greater than or equal to 0. So see, it satisfies that. It is closed under vector addition. But what about scalar multiplication? Now we let u equal u1, u2, 0, 0, and we let k equal -1. -1 is a scalar. Then k times u is equal to ku1, ku2, 0, 0. Well, it's not hard to see here now that k times u1 is negative, k times u2 is negative. That is not in S. So this is not a subspace. Because it violates the third condition. Scalar multiplication, you can do a scalar multiplication and you can get out of that set. That means it is not a subspace. A couple of properties of subspaces. First, Rn is a subspace of itself. So the entire set Rn, we do call it a subspace of itself. Okay? It does satisfy the three properties. And the second one, the zero set is a subspace of Rn. So what does this mean? Why is the zero, first off, what is the zero set, the zero space? The zero space is equal to the set, which is a single vector, which is the zero vector. Okay? So this is a set that has a single element in it. That's it, just the zero vector. Why is this a subspace? Well, think of the three conditions. The three conditions. First one is that the zero vector is in the space. That's true. The second, if you add anything together, add any two elements together, you stay in it. Well, what are the only elements? The only things you can add together are the zero vector plus the zero vector. And what do you get? The zero vector. So adding any two elements stays in the set. The third says that multiplying any scalar by any element in the set stays in the set. So if k is any scalar, multiply it by the zero vector, since that's the only thing in the set, what do you get? You get the zero vector back again. So you can't leave the set by multiplying by a scalar. That is a subspace. It satisfies the conditions of a subspace. We call it the zero subspace of Rn. Okay, so let's take a look at another example. We're going to let S be the set which is the span of these two vectors. And we're going to show that S is a subspace of R3. So to be a subspace, we have three conditions we have to satisfy. Our set is the span of these two vectors. So first off, first condition is zero in here? Well, what is the definition of the span of two vectors? It's the linear combination of the vectors. So if we take 0 times the first vector plus 0 times the second vector. What's that equal to? It's equal to the 0 vector plus the 0 vector, which is equal to the 0 vector. So the 0 vector is a linear combination of those two vectors. So it's in the set. What about the second condition? The second condition says that if you have any two vectors in your set in S, then adding them together doesn't leave the set. So let's pick any two vectors in here. But what is a vector in the set? Well, our set is the span of these two vectors. So the span of the vectors is a linear combination of them. So our first vector u is equal to something times the first vector plus another number times the second vector. That is the literal definition of an element of S. An element of S is a linear combination of those two vectors. So that gives us one vector. Now what about a second vector? Well, a second vector v, we do it the same way. v1 times our first plus v2 times the second. That is the description of any two vectors in our set S. Now, we're trying to show that this is a subspace, so we have to show that if we take these two vectors, add them together, we are still going to be in the set. So what happens? What's u plus v? Well, u plus v is u1 times our first vector plus u2 times our second vector plus v1 times our first vector plus v2 times our second vector. But now note we can take these things and rearrange them. That's u1 plus v1 times our first vector plus u2 plus v2 times our second vector. So what is this? This is a number times our first vector plus a number times our second vector. That is the definition of it being in the span. So this is closed under addition. What we did was we took u and v, that u and v are any vectors in the span, and we showed that if you add them together, you get another vector that's in the span. So that second condition is satisfied. What about the third condition? The third condition says that it's closed under scalar multiplication. So again, we're going to say u is any vector in that span. So it's u times 2 minus 1, 1, plus some other number times the second vector. So that's u. So that describes any vector in there. We're going to say k is a scalar. So now what happens if we take ku? K, so this saying any scalar times any vector, what do we get? So it's k times u1 plus 2 minus 1, 1 plus u2 times 1 minus 1, 2. Rearrange it a little bit. We get k times u1 times 2 minus 1, 1 plus k times u2 times 1, negative 1, 2. Well, what is this? This is a number times the first vector plus a number times the second vector. That is the definition of it being in the span. So we are closed under scalar multiplication. So S is a subspace. It satisfies the three conditions in the definition for a subspace. Okay, so let's look at another example. we're going to define something called the null space of a matrix. We're going to see the null space again later on. This is an important thing to know about, but we're going to define it here. The null space of a matrix is the set of solutions to AX equals 0, and it's denoted by null of A. So in other words, it's all of the vectors that when you multiply it by A, the product you get is 0. And let's see an example of this. So here's a matrix, this matrix A. We're going to find the null space and see what it looks like. So what's the null space? The null space is by definition everything that when you take this vector, multiply it by x1, x2, and x3, so some vector in R3, you end up with 0, 0. Okay? So now, how can we describe all of these vectors, x1, x2, and x3? What's the solution to this? This is a system of linear equations. We know how to solve this. How do we do it? We put it into an augmented matrix. And 0, 0. There is our augmented matrix. So now we have to solve this. So first pivot position, let's get rid of what's under there. So if we take row 1 minus 2 row 2 is the new row 2, what do we get? First row stays the same. The second row, that becomes 0, minus 3, minus 7, and 0. Okay, so we've taken care of that first column. The second column, that's our pivot point. So we are going to do 3 row 1 plus row 2 is the new row 1. What do we end up with? We end up with 6, 0, 3 times negative 1 minus 7 gives us negative 10, and a 0, we get 0, negative 3, negative 7, and 0. And now I'm going to get it into row reduced echelon form. I'm going to take it one step further. This requires two operations. I'm going to do them at once. If I take 1/6 of row 1 is the new row 1, and negative 1/3 of row 2 is the new row 2. You can do this as two steps if you want. I'm just combining them into one. We get 1, 0, negative 4 over 3, and 0. On the bottom row, we get 0, 1, 7 over 3, and 0. So there is our row reduced echelon form of our augmented matrix. Okay, so what does this mean now? So when I row reduced it, I got this matrix. I got that matrix. So now, let's take this and put it back into equation forms. Remember, this was x1, x2, and x3 columns because we were looking for the matrix or for the vector x1, x2, and x3 that when you multiplied by a gives you a 0. So what are the equations here? This is the equation. First row is x1 minus 4 over 3 x3 is equal to 0. The second one says that x2 plus 7 over 3 times x3 equals 0. And any variables, x1, x2, and x3, that satisfy these two equations are in the null space. This is the solution to our system of linear equations. So what does this look like exactly? Well, let's take this one step further and figure out if we can write this slightly differently. This is, if we rewrite this equation, what do we get? We get that x1, let me do it down here. We get that x1 is equal to 4 over 3 x3. We get that x2 is equal to negative 7 over 3 x3. And remember, we're looking for a vector x1, x2, x3. What does it say about x3? Well, x3 can just be whatever you want. It can be equal to x3. So this means that if you give me any number for x3, that x1 and x2 are set by these equations. What does this mean? This means that our vector x1, x2, and x3, which is a vector in the null space, is equal to something times 4 over 3, negative 7 over 3, and 1. So anything in our null space is a number, pick any number, times the vector 4 over 3, negative 7 over 3, and 1. What does this mean? This means that the null space of A, what we were looking for, is equal to the span of a single vector, 4 over 3, negative 7 over 3, and 1. Anything times that vector is going to give you something in the null space. A times that vector is 0. And that totally describes it because we solved that system of linear equations. Well, we already saw that the span of a vector, we saw an example with the span of 2 vectors. It works the same way. The span of a single vector is a subspace. So the null space of A is a subspace. Okay, this example brought together a couple of ideas. It's the idea of the subspace, plus it's introducing this idea of the null space, and we saw in here a new way of writing the solution to a system of linear equations. Okay, it's called writing it in parametric form. We're going to be doing this a lot more later, coming up with something like this. This is your first example of it, but this is showing that a null space is a subspace. That's the important thing for today. So here's a definition. The column space of a matrix is the span of its columns, and it's denoted by col of A. This is a subspace as well. So the span of a set of vectors is a subspace. So for example, show that the column space of this matrix is R2. In other words, that it's everything in R2. So in other words, the column space is equal to the span. So S is equal to the span of 2, 1, 1, 2, and negative 1, 3. And we know that the span of a set of vectors is a subspace. So this is a subspace. But now we're asking, is this column space equal to R2? In other words, can I do a linear combination of these two vectors, or of these 3 vectors, and that's a linear combination, and is this equal to u1, u2 for any u1, u2 scalars? In other words, no matter what you pick, can I build it? Can I get it from those 3 vectors? We know how to do this. We do our augmented matrix. And we look to see if we have a solution for any possible u2 and u1. So let's reduce it. Take row 1 minus 2 row 2 is the new row 2. 2, 1, negative 1 u. Row 1 minus 2 row 2 is 0, negative 3, negative 7, and it's u1 minus 2 u2. So there's the first one. Now for the second step, we are going to do 3 times row 1 plus row 2 is the new row 2. What do we get? Sorry, that's not the new row 2, it's the new row 1. Using the second pivot point, we get 6, 0, 3 times that, 6, 0, minus 10. And 3 times row 1, it's going to give us 4 times u1 minus 2u2. And the bottom row is 0, minus 3, minus 7, and u1 minus 2u2. Now, what is this telling us? Well, it's telling us that we have it's going to tell us that we have a solution to every possibility. No matter what you put in there for u1 and u2, you have a solution for it because you have a pivot row for all the rows. So the column space is equal to R2. No matter what you choose for u1 and u2, this is going to give you a solution. In fact, it's going to give you an infinite number of solutions. Another definition. Let V be a non-zero subspace. A basis for V is a linearly independent set in V that spans V. Now, basis is going to be a very important concept moving forward. We have seen that if you take the span of a number of vectors, that is a subspace. Now we're going to go back the other way. We're going to say that if we have a subspace, can we write it as the span of a set number of vectors? And that's going to be one of the questions that we're going to be looking at. So here's an example. The set of standard vectors. So what are standard vectors? The standard vectors are the vectors 1, 0, 0, 0, 0, 0, 1, 0, 0, and so on. These are a basis for Rn. So for instance, the standard basis of R3 are those vectors. You take any vector in R3, you can build it from a linear combination of those 3 vectors. So what you're saying is that any vector in R3 is a linear combination of those vectors. That's equal to u1 times 1, 0, 0, plus u2 times 0, 1, 0, plus u3 times 0, 0, 1. So those 3 vectors, the span of those 3 vectors is all of R3. You can build everything in R3 from the standard vectors. So another example. We have this matrix. We're going to look at the column space of this matrix. So anything that you can build out of the columns of this matrix. So we're looking at the span of 3 vectors. We have 3 vectors. Those are the 3 vectors of the column space. Is this a basis? A basis has to be linearly independent. But these vectors are not linearly independent. Okay? You should be able to see why these are not linearly independent, because there's a repeated vector in there. So that means that this is not a basis. A basis has to be linearly independent. If you take A, your vector A, and you row reduce it, what do you get? So we're not augmenting it, we're just taking the matrix A and we're row reducing. We get that. Where are our pivot elements in here? Our pivot elements are there and there. Columns 1 and 2. Go back to your original matrix, take column 1 and column 2, those columns form a basis. Okay? So if you have a set of vectors and you are looking at the span of those vectors and you want to see if it's a basis or not, in other words, if they are linearly independent, what do? You put them together, you row reduce, and you take the vectors that correspond to the columns where you have a leading element. Those form a basis. They are going to be linearly independent. In fact, this forms the basis of our next theorem, Theorem 13. Theorem 13 says that the pivot columns of a matrix A form a basis for the column space of A. So think about what this means. If A is a matrix and we are looking at the column space, in other words, everything you can build from the columns, but you want a basis. You want the basis, which is a linearly independent set of vectors that span the same thing. In other words, what are you doing? You're looking for if there are any vectors, any columns in there that are irrelevant, that are extra, that you don't need to form that column space. How do you do that? How do you figure them out? You take your matrix, you row reduce it, and you find all the pivot columns. Those columns are the important ones. Those are the ones you need. Any other column is just redundant. The ones that have a pivot column you pick those out and those form a basis. That's a linearly independent set of columns that span your column space. So here's another example. We're going to find a basis for this column space of A, where A is this set. Now, just looking at this set visually, you can't really tell offhand if the columns are linearly independent or not. So we have to figure out whether or not the columns are linearly independent. So we're going to take this matrix and we're going to row reduce it. Our rows are 3, 6, 8, 2, 4, 10, and 1, 2, 4. So what's the first thing we're going to do? We're going to take, I'm going to do this in slightly different order than we've been seeing. I'm going to take row 1 minus 3. Row 3 is the new row 3. I'm going to handle row 3 first. So 3, 6, 8, 2, 4, 10. And this gives us 0, 0, and minus 4. Next step, I am going to handle row 2. So 2 row 1 minus 3 row 2 is the new row 2. We get 3, 6, 8, 0, 0, and 24 minus 20, or minus 16 minus 30. 16 minus 30 gives us minus 14, 0, 0, and negative 4. Then if we take this and we do, what are we going to get here? 4 times row 2 minus 14 times row 3 is the new row 3. We get 3, 6, 8, 0, 0, negative 14, 0, 0, 0. Okay, so what do we have here? We have a pivot position there and a pivot position there. We can keep going with this to row reduced echelon form, but this is enough to show us where our pivot columns are. So what this says is that the column space of A is the span of the first and the third columns, 3, 2, 1, and 8, 10, 4. So that means that a basis for the column space of A is the set 3, 2, 1, and 8, 10, 4. You don't need all three vectors. Only two of the vectors will give you the column space. That is the basis. Okay, so that was an introduction to subspaces. We also touched on a couple of very important topics in here. Some things that we're going to see again later. Null spaces are going to be very important, and the idea of a basis is something that is going to be very important in upcoming lessons.